Welcome to the Pioneers Lecture Series, where we dig deep into the ideas changing your world. During the COVID-19 pandemic, a team of researchers called the R3T have been hard at work to rapidly understand the novel coronavirus using their science. We invited members of the R3T to talk about the ways they're helping humanity deal with the SARS-CoV-2 virus. Please welcome to the stage Professor Xin Gao.
Good afternoon, everyone. Glad to be here to talk about my research. My name is Xin Gao. I'm currently an associate professor in computer science program here at KAUST. I'm also the acting associate director for the Computational Bioscience Research Center here. So my group works on the intersection between computer science and biology. In particular, we are interested in developing novel computational methods and artificial intelligence techniques to solve a wide range of biological and biomedical problems. So naturally, during this COVID-19 crisis, we are taking the opportunity to make our own acid detection rates, whereas 88% of them have actually positive CT scans. And among the positive nucleic acid detection patients, the vast majority of them, 97% of them, also have positive CT scans. So these statistics tells us that CT scans can not only detect most of the positive nucleic acid detection rates, but can also detect a lot more COVID-19 patients. And therefore, there have been huge efforts and urgent development in AI-based computer-aided systems to develop CT scan-based diagnosis systems for emergent deployment to the frontline hospitals. The CT scan-based are the systems that can deal with both types. And from the extracted information or characteristics point of view, they can be classified into some expert manually extracted feature-based methods or automatically and systematically extracted feature-based methods. Usually for the second category, people have been using the main technology in AI, which is called deep learning. And talking about the AI-based CAD systems for COVID-19, apparently there have also been works that are based on X-ray and are based on CT scans. However, the frontline doctors have found out that in many cases, you actually need three-dimensional information for the accurate diagnosis for COVID-19. For example, some of the most famous characteristics for COVID-19, such as ground glass opacity and pulmonary nodule. These kind of features can only be visible in 3D images, which means CT scans become much more important diagnostic tools than X-ray for COVID-19. And there have been a number of methods and systems developed for CT scan-based COVID-19 diagnosis. Most of them belong to the category of classification, which means given a CT scan, the system can tell you whether this CT scan belongs to a COVID-19 patient or it belongs to a regular lung infection patient, or it belongs to a healthy person. That's called classification. On the other hand, there have been certain efforts on developing segmentation tasks, which means if I gave you a CT scan of a COVID-19 patient, I want your system to outline the boundaries of the infection regions, and furthermore, possibly calculate the infection volumes. This kind of tasks is called segmentation, which is naturally a much more challenging and much more difficult task than classification. So as of now, there has been only one segmentation method available, which uses this so-called human-in-the-loop strategy, which means the CAD system is trained to make some initial segmentation, and then the experts will manually refine and correct the system predictions and feed that back to the system to further get a better model. This is called human-in-the-loop. But if you look at all the existing methods, they share one or more of the following limitations. Number one, generalization power, which has been long as a well-known issue for AI-based systems. And the reason is that usually AI systems are trained on a well-annotated data set collected by one single platform, in this case, by one single CT scanner from a specific hospital. And the system can be trained to perform very well on this data set, but if you somehow transfer the model to another patient data sets from other hospitals or even in other countries, you see much poorer performance. And this is called generalization power. And the second one is limited data. Although there have been huge number of infected people all over the world for COVID-19, but the well-annotated and privacy protection data is still quite limited. And we know that AI-based methods, such as deep learning methods, they require a huge amount of data for training. So this will cause data scarcity issues. And the third one is most existing methods, they are focusing on the classification tasks, whereas the only segmentation task method requires high level of human intervention. So motivated by these limitations, we very recently developed a novel segmentation and quantification AI system for COVID-19 patients. And our system works particularly well for early stage patients, which are the most difficult subset of patients to deal with. So we started this entire project on March 30th this year. From when I formed a rapid response team within my group, consisting of 4 graduate students at KAUST. And these students started collecting data, annotating data, building systems, debugging systems, optimizing systems, benchmarking, evaluating, and finally drafting the paper, everything within 2 weeks. And then our paper went through several rounds of tough review process at the special issue for COVID-19 at this very top journal in medical imaging field called IEEE Transactions on Medical Imaging. And we are very proud that our paper was among the only 10 accepted papers from all over the world for this special issue. So our system is specifically designed to overcome the limitations that I just mentioned. Starting from the input data set, we first have this very important component called pre-processing component, for which we developed a method to project and embed any arbitrary CT scan dataset into the same standard space. And this pre-processing step will make our method to be machine agnostic, which means we actually do not care about which CT scan it is, from which CT scanner, from which hospital, or even from which country. We deal with them all together. And the second limitation is data scarcity, for which we developed this first COVID-19 data simulator. And the underlying assumption is that we obtained multiple CT scans for the same patient during different time points. And based on which, we can train a statistical model. And from this statistical model, we can sample as many CT scans as we want. And if our simulator is accurate, these simulated CT scans will become training data to feed the data-hungry deep learning models. And that will solve the data scarcity issue. And finally, we developed this novel segmentation method that uses predictions from multiple views together to get the final segmentation and quantification. So now let me briefly give you a little bit of technical details for those of you who are interested in knowing some details. So the first step is pre-processing. As we said that our CT scan data, like the blue cubic, can come from any platform under any configurations. So it is very important to cast and standardize them into the same space. And here, we define this standard space of size 334 by 334 by 512. And then we align this CT scan with this standard space by aligning their centers. And we will reshape this 3D tensor by keeping the voxel volume to be the invariant constant. And finally, we will also reshape or normalize the signal intensities by a linear transformation with respect to window level and window width. So after this step, our method will see all the input data sets in the same dimensionality and in the same format. Thus, it becomes machine agnostic. And the second important component in our method is called this simulator, for which we obtained CT scans from different stages of the same patient. For example, there I'm showing you the early stage image of a patient, and this is after 6 days, the progressive stage of the same patient. And this patient has 10 infection regions in his lungs. So that plot shows you the distribution of the infection intensities of the 10 infection regions, each curve representing one infection region. And this one shows you the same distribution, but after 6 days. And the plots in the middle shows you the overlay of the early stage and progressive stage for each of these 10 infection regions. And you can see that although the infection regions can be larger or smaller, they can have different morphologies, but their distribution patterns are quite conserved. And without getting into too much technical details, what you can do is you can build statistical model to describe this time course progression from one time point to the other time point. And then what you can do is you can sample as many intermediate time points as you wish, which becomes augmented data for our deep learning model. So the third important component is the segmentation task itself. Keep in mind that our data is 3D tensors. So intuitively speaking, the straightforward solution would be to directly use the 3D deep learning model. For example, 3D convolutional neural network or 3D UNet. But these 3D models are known to have large numbers of parameters, which usually cause overfitting issue. And they have slow convergence rate and high demand on memory. On the other hand, you can go with another extreme. That is, I do not care about the 3D information, but I decompose the problem into a stack of two-dimensional problems, for which you can use 2D models. But apparently, by doing so, you will lose information, which will cause decreased performance. And we developed this new method for which we call 2.5D models. The idea is to use multiple views from 2D models, in our case, 3 orthogonal views, along the XY plane, the YZ plane, and the XZ plane. The underlying assumption is, number one, when radiologists they are uncertain about the diagnosis, they also look at other different views to make their judgment. And number two, our human tissues, such as lung lobes, arteries, veins, trachea, and so on, they have much more regular shapes than the infection regions. So from one dimension, some of the human tissues may look like infections. But if you look at this from an orthogonal angle, such tissues will look quite differently from infections. So by integrating information from different views together, there is a much better chance to be able to distinguish which part is infection and which part is regular human tissue. And that's our 2.5D model. So in order to comprehensively evaluate the performance of our method, we used 3 categories of performance measures. The first one is to evaluate the segmentation performance, for which we have the ground truth segmentations of the infection regions. We also have the predicted segmentation regions by our method. And this category of performance measures, including DICE, recall, and worst-case DICE, measures how much overlap these two infection regions are to each other. For example, DICE tells you what is the percentage of the overlapping regions between the two. And the second category of performance measure is for quantification, for which we have the manually annotated percentage of the infection volume with respect to the total volume of the lung. We also have our calculated infection region volume, and we can calculate the predicted percentage. And this category of performance measures measures how close these two values are to each other. So for which we have root mean square error, the smaller the better, and Pearson correlation coefficient, the closer to 1, the better. And of course, as computational methods, we also care about the runtime and the memory cost. We have collected this relatively large data set containing roughly 200 CT scans from 140 COVID-19 patients. And that means for one patient, there can be multiple CT scans. And this data set was collected from 8 different CT scanners with different parameters in 5 hospitals in China and in Saudi Arabia, which means this is really a heterogeneous data set. So here I'm showing you some quantitative results. Let's start from the performance measures on segmentation, for which on the top left, we compared our method with the state-of-the-art 2D models, which is 2D UNet, 2.5D models, including HD UNet, MP UNet, and 3D models, which include 3D UNet and 3D VNet. As you can see that in terms of the dice, our method has a dramatically better performance than all the existing methods. And in terms of the recall, our method is slightly lower than that of HD UNet. But HD UNet only achieved this high recall value at the cost of a high false positive rate. And then we further evaluated the stage-specific segmentation performance, for which you can see that in terms of progressive stage and severe stage, our performance is not as significant as our improvement for the early stage patients. This is expected because for progressive and severe stage CT scans, it's trivial to decide and to segment the infection regions. The vast majority of the lung becomes infections. Whereas for early stage patients, it is very difficult to detect the subtle infection regions. But in reality, the frontline radiologists, they need most help to deal with early stage patients. So this is more important. And then in terms of the quantification performance, you can see that our method is highly accurate with root mean square error to be as low as 2.5% to the ground truth value. And the Pearson correlation coefficient is as high as 97%. So finally, in terms of runtime and memory comparison, it took our method roughly 6 hours to be trained on 4 GPU cards, but when you use it, it takes you only 15 seconds. So here I'm showing you some cases where the first 2 rows are 2 Chinese patients, and the second 2 rows are 2 Saudi patients. So the second column shows you the ground truth manual segmentation of the infection regions by experienced radiologists. Third column is our segmentation. And starting from the fourth column to the right are the segmentation regions predicted by the existing state-of-the-art methods. So as pointed out by the blue arrows, you can see that our method can not only accurately identify the infection regions, but more importantly, it can correctly discard the human tissues, like arteries and trachea. And here I'm showing you 3 cases for the early, for the progressive, and for the severe stage patients. So the second column shows you the segmentation results for each of our individual view predictors, denoted in red, blue, and green. So the message is that each of our individual view predictor is not good. It cannot segment the infection regions. But as I indicate in the third column, when you combine and integrate the results from 3 individual views together, you suddenly would be able to make a very accurate segmentation. So the green color in the third column shows the results of combining 3 individual views together, and you can see that it gives you very accurate segmentation, which you can further project it back to the 3D view for visualization. We further conducted ablation study, for which we tried to remove each of the 3 components from our method and see whether the performance changes. If the performance drops a lot, that means that component is critical to the success of our method. So here, we try to remove the pre-processing component, the multi-view component, and the data augmentation component. So clearly, removing each of them will have a big performance drop, which means all of the three components contributed significantly to the success of our method. And for each of these three cases, on the top right corner is the segmentation by removing the pre-processing step. On the left bottom corner is the performance after removing the data augmentation component. And the right bottom corner is the one that has all the three components enabled. So you can see that if you remove pre-processing or data augmentation, the system is unstable. It also causes a lot of false positive and false negatives. So other than making these technical developments and contributions, we also tried to directly apply and deploy this system to the frontline hospitals to really make our contributions during this pandemic period. So we have been deploying our system to the radiology department at King Faisal Specialist Hospital and Research Center in Riyadh, for which we got this feedback. The system has been applied on 32 COVID-19 cases. Except for 2 cases, our system achieved 100% accuracy on all the remaining cases. And on average, it took those frontline radiologists less than 1 minute to use our system to read a CT scan dataset. So they expect that this model will make an important contribution to chest imaging, especially with the current pandemic. So finally, I would like to thank my rapid response team, composed of 4 of my best students, Longxi, Zhongxiao, Juexiao, and Haoyang. They worked day and night, 20 hours a day for 2 weeks to make this happen. And we are very grateful to the generous support from KAUST to make this research happen. So my research is supported by my KAUST baseline funding, my CBRC CCF funding, KAUST CRG AI initiative, Smart Health initiative, and the Translation Fund. So finally, I would like to thank you all for your attention. I hope you all stay safe and healthy during this crisis, and I hope that we will be back to normal soon. Thank you.